Hello, friend. Welcome back. Or if this is your first time drifting here with me, welcome home. Some nights the universe feels heavier than it should. Stars pulse in rhythms we can't quite hear. Darkness stretches wider than any map. And somewhere hidden in that endless black, there are objects that were born to shine, but never truly could. They linger in the space between what is and what might have been. Not quite stars, not quite planets, just waiting. Tonight we are going to meet them, the failed stars, the brown dwarfs, the things that almost were. Before we begin our quiet journey into the shadows, if you find comfort in these soft explorations of the cosmos, you might like to stay a while. You can gently tap the like button, subscribe if you'd like more stories, whispered softly in the dark, and ring the little bell, not for noise, but so the next quiet night can find you again. Think of it as leaving a light on, so we can find each other when the world goes still. Now, let's drift. Imagine you're floating in the cold between stars, the kind of cold that doesn't just chill your skin, but makes the very atoms slow their dance. You're looking for light, any light, because that's what stars do. They shine, they burn. They announce themselves across billions of miles. But here in this particular pocket of space, something glimmers weakly. It's warm, yes. You can feel heat radiating from it if you drift close enough. But it doesn't blaze. It doesn't roar with fusion like our sun does every second of every day. It simply glows, faintly, like embers that never caught flame. This is a brown dwarf, a star that never truly shone. Scientists suggest these objects exist in a strange twilight realm of physics. They form the same way stars do, from vast clouds of gas and dust that collapse under their own gravity, spinning and heating as they shrink. Picture a cosmic ballet matter, swirling inward temperatures, rising pressure building. In most cases, if enough mass gathers, something extraordinary happens. The core grows so hot, so dense, that hydrogen atoms begin to fuse, releasing the light and energy that defines a star. That's what happened with our sun. That's what happened with every point of light you see on a clear night. But brown dwarfs fall short. They gather mass, yes. They collapse in heat. But they never cross that critical threshold about 0.08 times the mass of our sun. It's a precise line in the cosmic sand. Just below it, fusion never ignites. The core warms perhaps to a few million degrees, but not the 15 million degrees needed to sustain the fusion of hydrogen. So, the brown dwarf is born warm, glowing in infrared light. We can't see with our eyes, but slowly, inexorably, it begins to cool. Research shows they're more massive than the largest planets, heavier than Jupiter by at least 13 times. Yet they can't claim the title of star. They exist in between, in the margins, neither one thing nor another. Have you ever felt like you were meant for something, reached for it, but couldn't quite grasp it? The brown dwarfs know that feeling. They carry the blueprint of a star, the same ingredients, the same birth process, but lack the mass to fulfill that destiny. Some might call them failures, but perhaps that's too harsh. Perhaps they're simply different. There's something almost gentle about them when you think about it. They don't demand attention. They don't burn through their fuel in spectacular supernovae. They just exist quietly, radiating their stored heat into the void, dimming over billions of years. If stars are bonfires, brown dwarfs are candles left burning in an empty room, still giving light, still giving warmth, just softer. The name itself tells a story. Brown dwarf was coined by Jill Tarter in 1975, though the color is a bit misleading. If you could see one with your own eyes, it wouldn't appear brown at all. Depending on its temperature, it might glow a deep magenta or a dull red, or even appear almost invisible, radiating most of its energy in wavelengths our eyes weren't designed to detect. But brown was chosen to represent something earthy, something dim, something not quite stellar. A placeholder for the in-between. For decades, brown dwarfs were theoretical. Astronomers predicted they should exist based on the physics of stellar formation, but finding them proved nearly impossible. They're too dim to spot with optical telescopes and too cool to shine brightly even in infrared. It was like searching for shadows in the dark, whispers of objects that might be there if only we could learn to see differently. The universe, it seems, is full of things that hide in plain sight. We build bigger mirrors, more sensitive detectors, teach ourselves new ways of seeing. And slowly the invisible becomes visible. Consider the physics of it all. When a cloud of gas collapses, gravity pulls everything toward the center. As the material compresses, it heats up. This is basic thermodynamics. Squeeze anything hard enough, and it warms. In a forming star, this process creates what's called a protostar, a hot core wrapped in a cocoon of swirling gas. If the protostar gathers enough mass, the temperature and pressure at its heart eventually trigger fusion. Hydrogen nuclei, normally repelled by electromagnetic forces, are crushed together so violently that they overcome that repulsion and merge, forming helium and releasing tremendous energy. This is what makes stars shine. Brown dwarfs go through the same early stages. They collapse, they heat, they form protostars. But when the moment comes when the core should ignite, there's simply not enough mass to push the temperature high enough. The gravitational squeeze isn't quite strong enough. Fusion doesn't start, or if it does, it's only a brief flicker. Some brown dwarfs can fuse deuterium, a heavier isotope of hydrogen, because it requires lower temperatures. This burns for a few million years, a cosmic eye blink, and then it's over. After that, the brown dwarf has no internal energy source. It just radiates away the heat from its formation, slowly across ages. This is where the line blurs beautifully terrifyingly. Below, about 13 Jupiter masses, an object is considered a planet probably formed in a disk around a star. Above 80 Jupiter masses, it's a star fusing hydrogen. In between, we have brown dwarfs, and even their scientists suggest gradations. The coolest brown dwarfs, called Y dwarfs, have surface temperatures cooler than a hot summer day on Earth. They're warm only in the cosmic sense, nothing like the searing heat of the sun. It's humbling, really, how much variety exists in the universe. We think of stars as these grand, unchanging beacons, but the cosmos doesn't deal in absolutes. There are stars that barely made it, stars that shine feebly, stars that never quite became stars at all. Each one is a reminder that nature doesn't follow our categories. We draw lines planet, brown, dwarf, star, but the universe just is. Imagine being a brown dwarf. You're born from the same stellar nursery as your brighter siblings, those massive stars that will one day explode and seed the galaxy with heavy elements. You form alongside them from the same material, the same chaos. But while they ignite and blaze, you remain dim. You drift through the darkness, a solitary point of faint warmth. No planets orbit you, at least not usually, though some brown dwarfs have been found with companions. You're alone, cooling, fading over time scales so vast that human minds can barely grasp them. But you're still there. You still exist. You still matter. Scientists believe brown dwarfs might actually be quite common in our galaxy. Some estimates suggest there could be billions of them, drifting unseen in the spaces between stars. They don't contribute much light, so they're hard to census, but they add mass to the galaxy's subtle gravitational tugs that influence the motion of everything around them. In a way, they're the quiet majority, the unseen workers holding the cosmic structure together, never asking for recognition. There's poetry in that, don't you think? The idea that most of the universe's building blocks are things we can't even see. That the loudest, brightest objects, the stars we write songs about, are actually the exception. Most of the mass in the galaxy is dark, quiet, unassuming, doing its job without fanfare. Brown dwarfs teach us something important about existence. They remind us that not everything needs to burn brightly to have value. Not everything needs to shout to be heard. Some things just need to be, to occupy space, to contribute their small gravitational pull to the grand dance. And isn't that a comforting thought on a night like this, when the world feels too loud, too bright, too demanding? To know that even in the universe, there are things that simply exist quietly without needing to prove themselves. They were born to be stars, perhaps, but they became something else, and that's okay. They endure, they persist, they glow softly in their own way. The journey to understanding brown dwarfs has been one of patience and new perspectives. For years, astronomers looked up and saw only stars and planets. The idea that something could exist in between seemed strange, almost contradictory. But as technology improved, as infrared astronomy opened new windows into the cosmos, the brown dwarfs revealed themselves. Not all at once, not with grand announcements, but slowly, one faint glow at a time. It makes you wonder what else is out there waiting to be discovered. What other in-between things exist, hovering at the edges of our definitions, challenging us to see differently. The universe, it seems, is far stranger and more nuanced than we ever imagined. And perhaps that's the real beauty of it. Not the things we understand, but the things we're still learning to see. So, tonight as we begin this journey into the realm of failed stars, let's carry that sense of wonder with us. Let's appreciate the brown dwarfs, not for what they couldn't become, but for what they are. Quiet, persistent, warm, existing in their own right on their own terms. They almost were stars. But perhaps in their own way, there's something even more interesting. We've only just begun to understand these twilight objects, these cosmic wanderers caught between definitions. Their story is one of discovery, of learning to see what was always there hidden in the dark. It's a story of physics and poetry, of science and metaphor, of things that glow without burning. And now that we've met them, now that we've felt their quiet warmth in the cold of space, we can begin to ask deeper questions. How did we find them? What are they made of? What weather rages in their atmospheres? What secrets do they hold about the universe's past? The brown dwarfs are waiting patient as always to share their story. And we have all night to listen. There's a moment in every star's life that changes everything. A single instant when the core ignites, when fusion begins, when darkness transforms into light. But for some objects in the universe, that moment never comes. They gather, they compress, they heat. And then, nothing. The fire that should have been stays locked inside, unborn. This is where brown dwarfs begin their story, not with a bang, but with silence. Let's go back to the beginning. To the birthplace of stars. Picture a molecular cloud vast beyond comprehension, drifting through the galaxy. These clouds are sometimes called stellar nurseries, and the name fits. They're cold, dense regions of space filled with hydrogen, helium, and trace amounts of heavier elements, the raw materials of stars. The cloud is dark, nearly invisible, except when it blocks the light of stars behind it. But inside, gravity is working, always working, pulling matter together, particle by particle, creating pockets of higher density. Scientists suggest that turbulence in the cloud, shock waves from nearby supernovae collisions with other clouds, the spiral arms of the galaxy itself, creates these density variations. Once a pocket forms, gravity takes over. Matter falls inward. The pocket becomes a core, and the core begins to grow. This is how all stars begin. This is how our sun began 4.5 billion years ago. And this is how brown dwarfs begin too. At first, there's no difference. A forming brown dwarf and a forming star look identical in their early stages. Both are protostars, hot cores wrapped in envelopes of infalling gas. Both spin as they contract, flattening into disks. Both heat up from the compression, glowing dimly in infrared. For hundreds of thousands of years, they're indistinguishable. The universe hasn't yet decided what they'll become, but mass is destiny. As the protostar grows, adding more and more material from the surrounding cloud, it approaches a critical threshold. If it gathers at least 0.08 solar masses, about 80 times the mass of Jupiter, something remarkable happens. The temperature at the core climbs past 10 million degrees Celsius. At this point, hydrogen nuclei squeezed together by immense pressure overcome their natural electromagnetic repulsion and fuse into helium. Energy floods outward, the star ignites. Light pours into space, a star is born. Brown dwarfs never reach this point. They stop gathering mass too soon. Maybe the cloud they formed in didn't have enough material. Maybe gravitational competition with nearby protostars starved them of fuel. Maybe they were ejected from the cloud early before they could finish growing. Whatever the reason, they fall short. Their cores heat up, yes, to a few million degrees sometimes, but not enough. Not nearly enough. Research shows that many brown dwarfs can fuse deuterium, a heavier isotope of hydrogen, with one proton and one neutron instead of just one proton. Deuterium fusion requires lower temperatures than regular hydrogen fusion, about 1 million degrees instead of 15 million. So, for a brief period, perhaps a few million years, a brown dwarf does shine with fusion energy. But deuterium is rare, making up only a tiny fraction of the universe's hydrogen. It runs out quickly, and when it does, the brown dwarf is left with no fuel to burn, no core fusion to sustain it, only the heat from its formation slowly radiating away into the darkness. This is the defining tragedy of brown dwarfs, if we can call it that. They're born the same way stars are born. They follow the same process, obey the same physics dream, the same cosmic dreams. But they lack just enough mass to make those dreams real. It's like gathering kindling for a fire, stacking the wood, carefully striking the match. But the wood is just damp enough that the flame sputters and dies. The potential was there. The structure was there. But the conditions weren't quite right. Think about how precise this threshold is. At 0.075 solar mass as an object will never fuse hydrogen. It's a brown dwarf. At 0.085 solar masses, fusion ignites and burns for trillions of years. The difference is just 1% of the sun's mass, yet it determines entirely different fates. One becomes a star shining steadily across cosmic time. The other becomes a brown dwarf glowing for a while, and then fading into obscurity. Nature, it seems, operates on razor-thin margins. There's something almost unfair about it, isn't there? Two objects born in the same cloud from the same material at the same time. One crosses the line and becomes a star. The other falls just short and spends eternity cooling in the dark. But perhaps fairness is a human concept, one that doesn't apply to the universe. The cosmos simply is. Objects form according to the laws of physics without judgment, without intention. Some make it, some don't. And both are equally valid expressions of how matter behaves under gravity. Let's consider what happens inside a forming brown dwarf as it realizes, if you will, that it won't ignite. The core continues to contract under gravity heating as it does. Electrons in the atoms are squeezed closer together. Eventually, the material enters a state called electron degeneracy, where quantum mechanics takes over. The electrons can't be compressed any further without violating the Pauli exclusion principle, a fundamental rule of quantum physics that says no, two electrons can occupy the same quantum state. This degeneracy pressure halts the collapse. The brown dwarf reaches an equilibrium, supported not by fusion energy like a star, but by quantum mechanical resistance to further compression. This is why brown dwarfs, despite their mass, are roughly the same size as Jupiter. Whether a brown dwarf is 13 Jupiter masses or 70 Jupiter masses, its radius stays about the same, around 70,000 kilometers, similar to Jupiter's radius. Add more mass and the object just gets denser, not bigger. It's counterintuitive, strange, but it's a direct consequence of electron degeneracy. The same physics, incidentally, that keeps white dwarfs from collapsing into black holes. So, a brown dwarf settles into this state. No fusion, just quantum pressure holding it up. And from this point forward, its story is one of slow, inevitable cooling. The heat from formation, the warmth from deuterium fusion, if it had any, radiates into space. The brown dwarf dims. Over millions, then, billions of years, it grows colder and colder. Eventually, it might cool to the temperature of a planetary atmosphere, or even colder. But it never truly goes out, not entirely. It will continue radiating faint infrared light for timescales longer than the current age of the universe. Have you ever watched embers die in a fireplace? How they glow orange, then red, then a deep crimson barely visible in the darkness? That's a brown dwarf's life. A slow fade from bright infrared to dim, infrared to nearly invisible. No sudden death, no supernova, no dramatic finale. Just a gentle dimming across ages. Now, here's where it gets interesting. Because brown dwarfs form the same way stars do, they also form in the same places. Stellar nurseries don't just produce stars, they produce a whole spectrum of objects. Massive stars, medium stars, like our sun red dwarfs, brown dwarfs, and even free-floating planets ejected from forming solar systems. When astronomers look at star-forming regions like the Orion Nebula or the Taurus molecular cloud, they find brown dwarfs scattered among the young stars, sometimes dozens of them. In some cases, brown dwarfs form in binary systems, orbiting each other like stellar partners, even though neither is truly a star. Scientists have found brown dwarfs as young as 1 million years old, still surrounded by disks of dust and gas, just like young stars. Some of these disks might even form planets, though the physics of planet formation around such low-mass objects is still being studied. Imagine that a brown dwarf with planets, a failed star with its own miniature solar system. The universe's sense of irony is exquisite. One common misconception is that brown dwarfs are just large planets, but the distinction is important. Planets form in disks around stars, building up from smaller solid cores that accrete gas. Brown dwarfs form from the collapse of gas clouds like stars. The formation mechanism is different, even if the final mass can be similar. A 13 Jupiter mass object formed in a protoplanetary disk is a planet. The same mass object formed from a collapsing cloud is a brown dwarf. Same mass, different origin, different classification. It's a reminder that in astronomy, context matters. We can't always judge an object by its appearance alone. We have to understand its history, its birthplace, the process that brought it into being. There's also the question of how common brown dwarfs really are. Early estimates suggested they might outnumber stars filling the galaxy with faint, unseen masses. But surveys have shown they're less common than that. For every star, there might be one brown dwarf, maybe fewer. They're not rare, but they're not overwhelmingly abundant either. The galaxy is still mostly stars and planets, with brown dwarfs occupying a smaller niche. Still, even if they're a minority, their existence tells us something profound about star formation. It tells us that the process isn't clean or efficient. Not every collapsing cloud becomes a star. Some fall short. Some are disrupted. Some wander off into the galaxy alone, untethered to any stellar system. The universe is messy, improvisational, full of variations on a theme. And perhaps that's the real lesson of brown dwarfs. They're not failures in any meaningful sense. They're variations. They're the universe exploring every possibility, every permutation of mass and density and temperature. They exist because they can exist, because the laws of physics allow for objects that sit just below the threshold of stellar fusion. They're proof that nature doesn't have a blueprint with strict requirements. It has tendencies, probabilities, ranges. And within those ranges, everything that can happen does happen. So when we look at a brown dwarf, or try to, given how faint they are, we're looking at a what if. What if this cloud had gathered just a bit more mass? What if fusion had ignited? What would this object have become? But those questions miss the point. The brown dwarf isn't a failed star. It's a brown dwarf. Complete. Whole. Existing in its own right. Born without fire, yes, but born nonetheless. Warm, real. Drifting through the galaxy with quiet dignity. And now, knowing how they come to be knowing the precise physics that determines their fate, we can begin to ask how we ever found them in the first place. Because for decades, brown dwarfs were invisible to us, theoretical constructs that should exist but couldn't be seen. The story of their discovery is a story of persistence, new technology, and learning to see the universe in wavelengths our eyes were never meant to perceive. It's a story of finding ghosts in the dark. Imagine holding two objects in your hands. In your left hand, a planet massive, yes, but still a world. Still something that orbits a star, something that knows its place in a solar system. In your right hand, a star burning, fusing radiating light across the cosmos, defining itself by fire. Now, imagine there's something that fits in neither hand, something that slips between your fingers, refusing to be categorized. That's where brown dwarfs live, in the space between definitions, in the cracks of our understanding. The universe, it turns out, doesn't care much for our labels. We've talked about how brown dwarfs form how they fall short of stellar ignition. But what exactly are they? This question plagued astronomers for decades, and in some ways, it still does. Because to understand brown dwarfs, you have to understand boundaries, and boundaries in nature are rarely clean. Let's start with mass, because mass is where everything begins. At the low end, we have planets. Jupiter, the largest planet in our solar system, mass is about 1,000th that of our Sun, or roughly 318 times the mass of Earth. It's enormous by planetary standards, a gas giant with storms larger than Earth itself, but it's still unmistakably a planet. It formed in a disk of material around the young Sun, building up from a solid core that then captured hydrogen and helium from the surrounding nebula. At the high end, we have stars. The smallest stars, called red dwarfs, mass about 0.08 solar masses, 80 times Jupiter's mass. These tiny stars burn hydrogen slowly, efficiently, and can live for trillions of years, far longer than the current age of the universe. They glow red dim, but steady, fusing their fuel atom by atom across unimaginable timescales. Brown dwarfs exist in between. Research shows that the lower boundary sits around 13 Jupiter masses. Below this, an object likely formed as a planet and never experienced any fusion at all. Above 13 Jupiter masses, deuterium fusion becomes possible. The object can burn this rare isotope of hydrogen for a brief period, releasing energy glowing a bit brighter. This is one marker that separates brown dwarfs from giant planets. But 13 Jupiter masses is just a guideline, not a law. Some objects above this limit might still be planets if they formed in a protoplanetary disk. Some objects below it might be brown dwarfs if they formed from cloud collapse. The distinction gets blurry, especially when we're talking about free-floating objects with no parent star to provide context. Scientists suggest that the real dividing line isn't mass at all, but formation mechanism. If it formed like a star from a collapsing gas cloud, it's a brown dwarf. If it formed like a planet in a disk around a star, it's a planet. But when we observe an isolated object floating in interstellar space, how do we know which process created it? We often can't. We guess based on mass composition location. We make educated inferences, but certainty eludes us. This ambiguity is uncomfortable for astronomers who like neat categories. Yet, it's also beautiful in a way. It reminds us that nature is continuous, not discrete. The universe doesn't have sharp edges. It has gradients, transitions, overlapping regimes where multiple descriptions might apply. At the upper boundary, brown dwarfs are separated from stars by the hydrogen burning limit, 80 Jupiter masses or 0.08 solar masses. Cross this line and fusion ignites. Stay below it and fusion never happens, or happens only briefly with deuterium. This boundary is more reliable than the planetary one because it's based on physics, not formation history. Above 80 Jupiter masses, hydrogen fusion is inevitable. Below, it impossible. So brown dwarfs occupy this narrow range from about 13 to 80 Jupiter masses. It's a small window in cosmic terms, yet within it exists a remarkable diversity of objects. Some are hot, freshly formed, glowing brightly in infrared. Others are ancient, cooled to planetary temperatures barely visible at all. Some are solitary wanderers. Others orbit stars, or even other brown dwarfs. Some have weather systems, magnetic fields, maybe even moons. Let's pause and think about what it means to be in between. In human culture, being neither one thing nor another is often seen as problematic, as if lacking identity. But maybe it's the opposite. Maybe being in between means having the freedom to be something unique, something that doesn't fit existing molds. Brown dwarfs are heavier than any planet, yet they don't fuse hydrogen like stars. They're warmer than planets, at least when young, yet they cool over time like giant planets do. They can have atmospheres as complex as Jupiter's, yet they glow from internal heat like stars. They're chimeras, blending traits from both sides of the divide. One of the defining features of brown dwarfs is their ability to fuse deuterium. Deuterium is hydrogen with an extra neutron. Instead of one proton forming the nucleus, there's one proton and one neutron. This extra mass makes it slightly easier to fuse because the heavier nucleus has a higher probability of overcoming electromagnetic repulsion at lower temperatures. At around 1 million degrees Kelvin, deuterium fusion can occur. Regular hydrogen needs 15 million. For objects above 13 Jupiter masses, the core gets hot enough to ignite deuterium. The brown dwarf experiences a brief phase of fusion, maybe lasting a few million years. During this time, it generates energy internally, slowing its contraction and cooling. But deuterium is scarce, only about 20 parts per million in the universe's hydrogen. It runs out quickly. Once it's gone, the brown dwarf has no more fuel. It settles into a long decline, radiating away its residual heat. This fleeting moment of fusion is one of the few clear distinctions between brown dwarfs and giant planets. A 13 Jupiter mass brown dwarf will fuse deuterium. A 10 Jupiter mass planet will not. But again, the line is soft, not hard. Nature doesn't flip a switch at exactly 13 Jupiter masses. The transition is gradual. What about lithium? Here's another marker astronomers use. Lithium is a light element that gets destroyed at relatively low temperatures inside stars and brown dwarfs. If an object is massive enough to sustain high core temperatures, lithium gets depleted. But in low-mass brown dwarfs, lithium survives because the core never gets hot enough to destroy it. By measuring lithium in an object's spectrum, astronomers can infer whether it's a brown dwarf or a very low-mass star. This is called the lithium test, and it's been used since the 1990s to confirm brown dwarf candidates. It's a bit like detective work. You can't see inside, the object can't measure its core temperature directly. But you can look at what elements are present in its atmosphere and work backward, inferring what must be happening deep inside. Now, here's where things get philosophically interesting. If you found an isolated object floating in space, 70 Jupiter masses, no star nearby, how would you classify it? It's below the hydrogen burning limit, so it's not a star. But did it form like a star or get ejected from a planetary system? Without knowing its history, you can't be sure. Astronomers would probably call it a brown dwarf based on mass alone. But there's an inherent uncertainty. Some researchers have proposed the term sub-brown dwarf, or planetary mass object, for things below 13 Jupiter masses that formed like brown dwarfs. Others prefer to just call them brown dwarfs and acknowledge the spectrum. The terminology is still evolving, still being debated. Language struggles to keep up with discovery. Consider how this mirrors our own experience of identity. We like to put people in categories: artist, scientist, teacher, but most of us are mixtures, combinations, in-betweens. We resist simple labels. Brown dwarfs are the same. They resist simple labels. They exist in a space where multiple descriptions overlap, where the question, "What is this?" doesn't have one neat answer. There's also the matter of temperature. Young brown dwarfs can be quite hot, over 2000 Kelvin, at the surface hotter than many stars. But they cool over time. A billion-year-old brown dwarf might be only a few hundred Kelvin cooler, than an oven approaching room temperature. At this point, is it still meaningfully different from a giant planet? It's the same temperature, roughly the same size, but it formed differently, and that formation history matters. Scientists believe that studying brown dwarfs helps us understand both stars and planets. They're a bridge between two regimes of astrophysics. By observing how their atmospheres behave, how they cool, what weather patterns emerge, we gain insights into the atmospheres of gas giant exoplanets, which are too faint to study in detail. Brown dwarfs are brighter, easier to observe, and they serve as proxies laboratories for testing our models of planetary atmospheres. In a way, brown dwarfs are generous. They didn't become stars, but they help us understand stars. They're not planets, but they help us understand planets. They give more than they take. Here's a thought experiment. Imagine two objects, both 70 Jupiter masses. One formed from a collapsing cloud fragment. The other was ejected from orbit around a star during a gravitational interaction. Are they the same thing? They have the same mass, the same composition, likely the same temperature and size. Yet their origins differ. Does that difference matter? Astronomers would say yes. Origin informs classification. But physically, the two objects are identical. They would evolve the same way, cool at the same rate, emit the same spectrum of light. The universe doesn't distinguish between them. Only we do. This raises a deeper question about what we mean when we classify celestial objects. Are we describing the objects themselves, or are we describing our understanding of them? Are our categories real, or are they just convenient fictions we use to organize knowledge? Brown dwarfs challenge us to think about these questions. They don't fit neatly into boxes. They sprawl across boundaries, embodying ambiguity. And maybe that's their greatest gift to science, not just new data, but new humility. A reminder that the universe is more complex, more nuanced, more wonderfully messy than our theories can ever fully capture. There's comfort in that, strangely, in knowing that no matter how much we learn, there will always be edges where our understanding frays objects that don't quite fit mysteries that refuse to be solved cleanly. The universe keeps us honest. It keeps us curious. So, when we look at brown dwarfs, we're not just looking at failed stars or overgrown planets. We're looking at something genuinely in between, genuinely unique. Objects that remind us that boundaries are human constructs, useful, but ultimately arbitrary. The cosmos doesn't recognize our categories. It simply creates endlessly every variation allowed by physics. And perhaps that's the point. The universe doesn't ask permission to be complicated. It doesn't apologize for blurring lines. It just is in all its strange, contradictory, beautiful complexity. Brown dwarfs are proof of that. They exist because they can. They occupy a niche because that niche is there to be occupied. They're neither star nor planet, and in being neither, they become something else entirely, something worth knowing, something worth seeking in the darkness. Which brings us to the question that haunted astronomers for decades. How do you find something that barely glows, that hides in the gaps between stars, that exists in wavelengths invisible to human eyes? How do you discover the undiscoverable? For 30 years, brown dwarfs were ghosts, predicted by theory, supported by mathematics, but never seen. Astronomers knew they should exist the way you might know. There's something moving in a dark room, even though you can't see it. The equations said they were out there. The physics demanded it. But finding them, that was another matter entirely. Because how do you photograph something that doesn't want to be found? The story of discovering brown dwarfs is really a story about learning to see differently, about building new eyes. It begins in 1963 with a young astrophysicist named Shiv Kumar working at the University of Virginia. Kumar was studying stellar evolution, particularly what happens at the low mass end of the stellar spectrum. He was running calculations exploring what would occur if a star-like object simply didn't have enough mass to sustain hydrogen fusion. His equations kept returning the same answer. Such an object would form, heat up briefly, then cool indefinitely. It would glow but faintly, mostly in infrared wavelengths. It would be a star that wasn't quite a star. Kumar published his findings, introducing the theoretical concept of these substellar objects. He didn't call them brown dwarfs, yet that name would come later, in 1975, coined by astronomer Jill Tarter. But the foundation was laid. The universe Kumar suggested might be filled with objects that slipped between planets and stars, invisible to optical telescopes, but real nonetheless. The problem was proof. How do you prove something exists when you can't see it? For decades, astronomers searched. They pointed telescopes at nearby star-forming regions, hoping to catch a glimpse of something too faint to be a star, but too luminous to be a planet. They came up empty again and again. Brown dwarfs, if they existed, were masters of hiding, too cool to shine in visible light, too small to be detected by the crude infrared detectors of the time. They became almost mythical, the astronomy equivalent of Bigfoot, theoretically possible, but frustratingly elusive. Some astronomers began to doubt. Maybe the theories were wrong. Maybe brown dwarfs didn't exist after all. Maybe there was some process that prevented objects from forming in that mass range, some mechanism that forced clouds to either become full stars or remain as planets with nothing in between. But others kept searching, because the math was too elegant to ignore, the physics too compelling. The breakthrough came in the mid-1990s, and it came because of two things: better infrared technology and larger sky surveys. Infrared astronomy had advanced significantly. New detectors could sense heat that earlier instruments missed. Astronomers realized that if brown dwarfs existed, they'd be radiating most of their energy in the near-infrared wavelengths, just beyond what human eyes can see. It's like how a cooling piece of metal glows red, then fades from view, but it's still radiating heat. Brown dwarfs were past the visible glow, deep into the heat-only phase. In 1995, two teams made announcements that changed everything. The first was a team led by astronomers at Caltech and Johns Hopkins. They identified an object in the Pleiades star cluster called Tidy-1. Spectroscopic analysis showed it had lithium in its atmosphere, the telltale signature of a brown dwarf. Lithium gets destroyed in stars, but survives in brown dwarfs because their interiors never get hot enough. Tidy-1 had lithium. It was too cool to be a star. It was exactly what Kumar had predicted 3 decades earlier. Almost simultaneously, another team using the Palomar Observatory discovered an object orbiting a star called Gliese 229. They designated it Gliese 229b. This object was even more convincing. Its spectrum showed methane, a molecule that shouldn't exist in any star's atmosphere because stars are too hot. Methane breaks apart above about 1,300 Kelvin. But brown dwarfs, especially cooler ones, could have methane. Gliese 229b did. Its mass was estimated between 20 and 50 Jupiter masses. Too massive to be a planet. Too cool to be a star. Brown dwarfs were real. The ghosts had been found. Do you remember the first time you solved a puzzle you'd been working on for hours, maybe days? That moment when the pieces finally clicked into place. Imagine that feeling, but stretched across 3 decades of searching, thousands of astronomers, countless nights staring at the sky. The discovery of brown dwarfs wasn't just scientific triumph, it was validation, proof that patience, persistence, and the right tools can reveal what's hidden. After 1995, the floodgates opened. With the knowledge that brown dwarfs were real and detectable, and infrared astronomers launched dedicated surveys. The 2-micron all-sky survey, known as 2MASS, scanned the entire sky in near-infrared wavelengths. It found hundreds of brown dwarfs, cataloging their positions, temperatures, and properties. Later, NASA's Wide Field Infrared Survey Explorer, WISE, found even cooler ones, pushing into the realm of Y dwarfs, brown dwarfs with temperatures comparable to a warm summer day on Earth. Each discovery refined our understanding. Brown dwarfs weren't rare curiosities. They were a fundamental part of the cosmic population scattered throughout the galaxy, outnumbered by stars, but present in significant numbers. Some estimates suggest there might be 10 billion brown dwarfs in the Milky Way, maybe more. They'd been there all along, invisible, waiting for us to develop eyes that could see them. One of the most remarkable discoveries came in 2013. Astronomers identified a binary brown dwarf system called Lumen 16, located just 6.5 light-years from Earth. This made it the third closest stellar system to our Sun, after Alpha Centauri and Barnard's star. For context, 6.5 light-years is extraordinarily close in cosmic terms. It's our immediate neighborhood. And yet, we didn't know Lumen 16 existed until 2013. For all of human history, these two brown dwarfs had been there nearby, unnoticed. Think about that for a moment. Our closest neighbors, and we didn't see them until we learned to look in infrared. Lumen 16 consists of two brown dwarfs designated Lumen 16A and Lumen 16b, orbiting each other every 27 years or so. Their masses are estimated around 30 to 40 Jupiter masses each. They're cool about 1,300 Kelvin for Lumen 16A and slightly cooler for Lumen 16b. Because they're so close to Earth, astronomers can study them in detail. They've even mapped weather patterns on Lumen 16b's surface, watching storms evolve over time. It's the kind of study that would be impossible for a brown dwarf farther away. The discovery of Lumen 16 also highlighted something humbling. Our census of the local universe is still incomplete. We don't know everything that's nearby. There might be more brown dwarfs lurking within a few light years, too faint for current surveys to detect. The neighborhood is bigger and stranger than we realized. Another fascinating aspect of brown dwarf discovery is the role of citizen scientists. In recent years, projects like Backyard World's Planet 9 have invited the public to help search for brown dwarfs in archival telescope data. Volunteers examine images looking for faint moving objects that automated algorithms might miss. And it works. Citizen scientists have discovered dozens of brown dwarfs, some of the coolest and closest examples known. It's a reminder that discovery isn't reserved for professionals with PhDs. Sometimes it just takes patient eyes and a willingness to look. There's also the story of WISE J0855110.83 minus 0714442.5. One of the coldest brown dwarfs ever found. Discovered by WISE in 2014, this object has a temperature estimated around 225 to 260 Kelvin. That's minus 48 to minus 13 degrees Celsius, colder than Antarctica in winter. It's so cool that its atmosphere likely contains water clouds or possibly even clouds of ammonia ice. It's more like a giant planet than a star. Yet it formed in isolation, not in orbit around anything. A frozen wanderer drifting through space. The name, by the way, WISE J085510.83 minus 0714442.5, is typical of astronomical designations. It encodes the telescope that found it WISE and its coordinates in the sky. Not poetic, but functional. Astronomers deal with thousands of objects. Poetry gets sacrificed for precision. Discovering brown dwarfs also required astronomers to rethink their assumptions about what stars look like. For centuries, stars were points of light in visible wavelengths. But brown dwarfs taught us that the universe has objects we can only see if we look in the right part of the spectrum. It's analogous to realizing that birdsong extends into ultrasonic frequencies humans can't hear. The world was always richer than we perceived, we just needed better instruments. This shift in perspective was profound. It meant that optical astronomy, for all its history and success, was showing us only part of reality. Infrared astronomy revealed another layer, one populated by cool stars, brown dwarfs, and dust clouds. Ultraviolet astronomy revealed yet another full of hot stars and energetic processes. Each wavelength was a different window into the cosmos. None was more real than the others. Each showed a different truth. Brown dwarfs exemplify this. In visible light, they're nearly invisible. In infrared, they glow clearly. They haven't changed. We have. We've learned to see what was always there. There were false alarms along the way, of course. Objects that seemed like brown dwarfs but turned out to be something else. Distant galaxies, cool, stars, instrumental artifacts. Each false alarm refined the search techniques. Astronomers learned to distinguish genuine brown dwarfs from imposters by looking at multiple wavelengths, studying spectra, measuring proper motion across the sky. It was painstaking work, but it paid off. One common mistake early on was confusing very low-mass stars with brown dwarfs. The boundary, as we have discussed, is around 80 Jupiter masses, but observationally distinguishing a 75 Jupiter mass brown dwarf from an 85 Jupiter mass red dwarf is difficult. Both are cool, both are faint. Only detailed spectroscopy measuring the presence or absence of lithium or methane can tell them apart. Many objects initially classified as brown dwarfs were later reclassified as stars and vice versa. The boundary is real in theory, but blurry in practice. What does it feel like to be an astronomer in the 1990s, finally seeing confirmation of something theorized for 3 decades? The journals don't convey that emotion, but you can imagine it. Relief, certainly, excitement, but also curiosity. Because now the real work begins. Now that we know brown dwarfs exist, we can ask deeper questions. What are they made of? How common are they? What do their atmospheres look like? Do they have weather? The discovery phase was just the beginning. Each answer spawned 10 new questions. And here's what's beautiful. We're still in the discovery phase. Every year, new surveys find fainter, cooler, more distant brown dwarfs. The census grows, the population becomes clearer. We're mapping a previously invisible component of the galaxy, filling in gaps on the cosmic map. It's exploration in the truest sense, charting unknown territory. Brown dwarfs remind us that the universe still holds secrets, that no matter how much we've learned, there's always more to find. They spent billions of years in the dark waiting for creatures on a small planet to develop the technology to see them. And when we finally did, they welcomed us into a wider, stranger, more complex cosmos. The ghosts became real, the invisible became visible, and the universe once again revealed itself to be richer than we imagined. But seeing them was only the first step. Understanding them, the physics of their cooling, the chemistry of their atmospheres, the categories we use to describe them, that required an even closer look. A look that revealed something extraordinary. Brown dwarfs don't just fade uniformly. They pass through distinct phases, each with its own signature, its own character. They cool like embers. Yes, but embers of different colors. There's a moment when fire becomes ash. Not suddenly, but gradually, through shades of red and orange and finally gray. The heat remains even when the light is gone. You can still feel warmth rising from what used to burn. Brown dwarfs live in that moment, stretched across billions of years. They don't burn out. They fade, passing through colors we've learned to name, stages we've learned to recognize. Each temperature tells a story. Each spectrum whispers what's happening in their cooling atmospheres. And astronomers, patient listeners, have learned to hear those whispers. Once brown dwarfs were discovered, the next challenge was understanding them. Not just finding them, but categorizing them. Mapping the journey of their cooling. Stars have spectral classes, O, B, A, F, G, K, M, each letter representing a temperature range and characteristic features in the star's light. These classes were established over a century ago, refined through decades of observation. But brown dwarfs were too cool to fit into the existing system. The coolest stars, M dwarfs bottom out around 2,500 Kelvin. Brown dwarfs kept going cooler. New categories were needed. Enter the L, T, and Y dwarfs. Extensions of the stellar alphabet reaching into temperatures no true star could achieve. L dwarfs were the first edition defined in the late 1990s, shortly after the initial brown dwarf discoveries. These are the warmest brown dwarfs, with temperatures ranging from about 1,300 to 2,000 Kelvin. At the hot end, they overlap with the coolest M-dwarf stars, creating some ambiguity. But as you move down the temperature scale, L-dwarfs become distinctly substellar. Their spectra show strong absorption lines from metals like sodium and potassium, which exist as neutral atoms in their atmospheres. The light they emit is deep red, almost crimson, though still radiating most energy in the near-infrared. Research shows that L-dwarfs also display dust clouds in their atmospheres. At these temperatures, grains of iron silicate and other refractory materials can condense out of the gas, forming hazes. Imagine clouds made not of water, but of vaporized rock and metal floating in the atmosphere of an object that's slowly dying. It's alien, beautiful, strange. The dust absorbs light at certain wavelengths, creating distinctive patterns in the spectrum that help astronomers identify L-dwarfs even at great distances. As an L-dwarf cools over millions of years, it transitions into the T-dwarf class. This happens around 1,300 Kelvin, a critical temperature where methane begins to dominate the spectrum. Methane is a simple molecule, one carbon atom bonded to 4 hydrogen atoms. It's stable at lower temperatures but breaks apart when things get too hot. In T-dwarfs, conditions are just right. Methane condenses in the atmosphere, creating thick clouds that absorb light strongly in the near-infrared. This gives T-dwarfs a characteristic appearance in spectroscopy deep methane absorption bands that earlier hotter brown dwarfs lack. T-dwarfs range from about 700 to 1,300 Kelvin. At the warm end, they're still glowing a dull red. At the cool end, they're almost invisible in optical light, radiating mostly in mid-infrared wavelengths. The dust clouds that characterize L-dwarfs have largely settled below the visible atmosphere. What remains is a clearer methane-rich layer. The brown dwarf is quieter now, cooler, less chaotic. The transition from L to T is marked by this clearing of the atmosphere, a kind of cosmic simplification. Scientists suggest that the boundary between L and T dwarfs represents a fundamental shift in atmospheric chemistry. Above 1,300 Kelvin, dust dominates. Below it, methane takes over. It's analogous to how water behaves differently above and below its freezing point. Same substance, different phase, different properties. Brown dwarfs don't freeze, but they do change character as they cool. And then, at the very coldest end, we have Y dwarfs. These were only confirmed in 2011, discovered by the WISE Space Telescope during its infrared survey of the sky. Y dwarfs have temperatures below 700 Kelvin, with the coldest examples approaching 250 Kelvin, or even lower. That's about minus 23 degrees Celsius, colder than the coldest natural temperature ever recorded on Earth. At these temperatures, brown dwarfs are barely glowing. They emit almost no visible light, only faint infrared radiation from their residual internal heat. Y dwarfs are extraordinary because they challenge our definitions yet again. They're so cool that their atmospheres resemble giant planets more than stars. Ammonia clouds, water clouds, possibly even exotic ices form in their upper layers. Their spectra show absorption from molecules like ammonia and water vapor signatures we also see on Jupiter and Saturn. Yet Y dwarfs formed like stars from collapsing gas clouds, not in protoplanetary disks. They're planetary in temperature, but stellar in origin. Consider the coldest Y dwarf discovered so far. WISE 0855-0714. Its temperature is estimated at around 225 Kelvin, roughly minus 48 degrees Celsius. That's colder than dry ice. At this temperature, water exists as ice in the atmosphere. Scientists believe WISE 0855 might have weather systems driven by water clouds raining or snowing in slow, ponderous cycles. It's a world of ice floating alone in space, generating no fusion, harboring no planets, just existing quietly at the edge of detectability. Imagine that. An object as massive as Jupiter, maybe 50 or 60 times more massive but cooler than the Arctic. Drifting through interstellar space, invisible to optical telescopes, barely visible even in infrared. If you could somehow stand on its surface, though, there's no solid surface to stand on, you'd feel a deep, pervasive cold. Not the cold of space, which is almost absolute zero, but a gentler cold, the kind that seeps into your bones. And above you, if brown dwarfs have skies, you could see clouds of ice crystals might drift, catching the faint glow of distant stars. It's achingly lonely in a way, but also serene. The naming convention LTY might seem arbitrary, but it follows the logic of stellar classification. When astronomers first categorized stars, they used letters based on the strength of hydrogen lines in the spectrum. Later, they reordered the sequence by temperature, giving us O, B, A, F, G, K, M. The letters don't spell anything, they're just labels. When brown dwarfs required new categories, astronomers simply extended the alphabet. L comes after M, T comes after L, Y comes after T. Simple, systematic, if a bit inelegant. There's talk of adding even cooler classes if we find brown dwarfs that have cooled below 200 Kelvin, though at that point, they'd be almost impossible to detect. The letter after Y would be, well, astronomers haven't decided. Maybe they'll start over with new symbols, or maybe they'll just call them ultra-cool Y dwarfs. The universe doesn't care what we name things. What's remarkable is how much information we can extract from a spectrum by analyzing the light, or rather the lack of light at certain wavelengths. Astronomers can determine temperature composition, atmospheric structure, even weather patterns. Each molecule absorbs light at specific wavelengths, like a fingerprint. Methane absorbs here, water absorbs there, ammonia over there. By comparing the observed spectrum to laboratory measurements and theoretical models, we can reconstruct what's happening in an atmosphere we'll never visit orbiting, or rather not orbiting a star we'll never see. It's detective work at a cosmic scale, reading invisible ink written in infrared. The transition from L to T to Y isn't abrupt. Brown dwarfs don't suddenly jump from one category to another. They cool gradually over hundreds of millions or billions of years, passing through intermediate states. An early T dwarf still has some characteristics of a late L dwarf. A late T dwarf begins to show hints of Y dwarf features. The boundaries are fuzzy, defined more for our convenience than because nature draws sharp lines. This gradual cooling is driven by basic thermodynamics. A brown dwarf has no internal energy source after deuterium fusion runs out. It's like a hot stone pulled from a fire and left to cool. At first, it cools quickly, radiating heat into space. But as it gets cooler, the cooling slows. Heat radiation depends on temperature. Hotter objects radiate more efficiently. As the brown dwarf dims and cools, it loses heat more slowly. Eventually, the cooling becomes glacially slow, taking billions of years to drop even a few hundred degrees. Scientists believe that the oldest brown dwarfs in the galaxy, formed over 10 billion years ago, might have cooled to temperatures comparable to the human body, around 300 Kelvin, or even lower. These ancient objects would be extraordinarily difficult to find. They'd emit almost no infrared light, fading into the background glow of the galaxy itself. But they're out there somewhere, relics of the early universe, cooling in silence. There's something poignant about that journey, from formation at thousands of Kelvin glowing warmly to eventual cold at temperatures where ice can form, from visibility to invisibility, from youth to old age stretched across time scales that dwarf human history. A brown dwarf born when the Milky Way was young is still cooling now, still fading, still journeying toward absolute cold. It's patient. It's inevitable. It's the long, slow goodbye of an object that never quite lived, but also never quite died. Have you ever watched a sunset and noticed how the colors change? The bright yellow of midday sun fades to orange, then red, then deep, purple, then darkness. Brown dwarfs undergo a similar progression. But instead of minutes, it takes eons. And instead of disappearing entirely, They linger in the infrared, glowing faintly unwilling or unable to let go completely. One interesting aspect of the LTY sequence is how it helps us understand exoplanet atmospheres. Giant exoplanets, especially young ones that are still hot from formation, have atmospheres very similar to brown dwarfs. Jupiter-mass planets orbiting distant stars might have temperatures of 1,000 Kelvin or higher if they're close to their parent star or still contracting. By studying brown dwarfs, which are easier to observe because they're not lost in the glare of a nearby star, astronomers learn how to interpret exoplanet spectra. Brown dwarfs are laboratories' test cases for understanding worlds we can barely detect. This is one of those beautiful instances where studying one thing illuminates another. Brown dwarfs help us understand planets. Planets help us understand brown dwarfs. The universe is interconnected in ways that only become apparent when you look closely. Classifying brown dwarfs also revealed unexpected diversity. Not all L dwarfs are the same. Some have more dust, some less. Some rotate rapidly, completing a full rotation in just a few hours. Others spin slowly. Some show evidence of strong magnetic fields emitting radio waves. Others are radio quiet. Within each spectral class, there's variation individuality. No two brown dwarfs are identical, just as no two stars are identical. This individuality extends to binary brown dwarf systems, where two brown dwarfs orbit each other. Lumen 16, which we mentioned earlier, is one example. Lumen 16A is an L dwarf, while Lumen 16B is a T dwarf. They're companions bound by gravity, but they're in different spectral classes. This tells us they have different masses, since mass determines cooling rate. The more massive one is still in the L phase, while the less massive one has cooled into T. Over time, both will continue cooling, eventually becoming Y dwarfs. But for now, they're mismatched, a cosmic odd couple. Studying binaries like Lumen 16 allows astronomers to test theoretical models of brown dwarf evolution. If the models are correct, the observed properties of both objects should be consistent with them forming at the same time from the same cloud. And indeed they are. The models work. The universe makes sense, at least in this small corner. There's also the phenomenon of spectral variability. Some brown dwarfs show changes in their spectra over time on timescales of hours to days. This is thought to be caused by weather storms, clouds' atmospheric circulation patterns that move across the visible hemisphere as the brown dwarf rotates. When a storm system rotates into view, the spectrum changes slightly. When it rotates out of view, the spectrum returns to its baseline. By monitoring these variations, astronomers can map the surface features of brown dwarfs, creating rudimentary weather maps for objects dozens of light years away. It's astonishing, really. We can't see these objects as disks. Even the closest brown dwarfs are just points of light. But by carefully analyzing how their light changes, we can infer what's happening on their surfaces, where storms rage and clouds drift. We're mapping invisible worlds using only the language of light. The L, T, and Y classification scheme is still evolving. New discoveries push the boundaries. Some objects seem to fall between categories showing hybrid characteristics. Astronomers propose subclasses early L, mid L, late L, and so on to capture finer distinctions. The system becomes more granular, more detailed, as our observations improve. And yet beneath all the classification, the naming, the spectral analysis, there's a simple truth. Brown dwarfs cool. They start warm and grow cold. They pass through stages each defined by temperature, each marked by the molecules that can survive in their atmospheres. Their embers fading in slow motion across cosmic time, from L to T to Y, from red glow to infrared whisper to near silence. It's a journey every brown dwarf takes alone or in pairs seen or unseen. A journey from almost star to almost planet, from heat to cold, from light to shadow. And all the while, they carry their stories with them, encoded in their spectra, waiting for someone to listen. But their cooling isn't the only drama unfolding in their atmospheres. Because as they fade, something else emerges: weather. Violent, chaotic, beautiful weather, unlike anything we experience on Earth. Imagine a hurricane with nowhere to make landfall. Winds screaming at thousands of kilometers per hour, clouds of molten iron swirling in perpetual motion, lightning crackling through atmospheres thick with vaporized rock. And it never stops. No continents to slow it down, no oceans to absorb its energy. Just endless circulation storms chasing storms across a sphere of gas that will never know calm. This is weather on a brown dwarf, violent, relentless, and utterly alien. And somehow, across the vast distances of space, we've learned to watch it unfold. When we think of weather, we think of Earth: rain, snow, sunshine, wind. Systems that move across landscapes that change with seasons that eventually dissipate. But brown dwarfs have no seasons. They have no land. They're massive spheres of hydrogen and helium, heated from within by the fading warmth of their formation, rotating rapidly in the void. And within their atmospheres, weather happens on a scale that makes Earth's most powerful storms look gentle. The study of brown dwarf weather is relatively new, emerging in the 2000s as telescopes became sensitive enough to detect variations in their light over time. Scientists noticed that some brown dwarfs brighten and dim in regular patterns, cycling every few hours. At first, this was puzzling. Stars don't usually vary that quickly unless they're pulsating or being eclipsed by a companion. But these brown dwarfs were isolated with no companions to eclipse them. The variations had to come from the objects themselves. The answer, research shows, is weather. Specifically clouds moving across the visible hemisphere of the brown dwarf as it rotates. When a bright region rotates into view, we see more light. When a dark storm system or thick cloud layer rotates into view, the brown dwarf dims slightly. By measuring these brightness changes over time, astronomers can map the distribution of clouds and storms, creating weather maps for objects that are dozens or even hundreds of light years away. It's extraordinary when you think about it. We can't resolve brown dwarfs as disks even with the most powerful telescopes. They're too far away, too small. But we can still map their weather by watching how their light changes. It's like trying to understand what a distant lighthouse looks like by studying how its beam sweeps past you. You never see the lighthouse directly, but you can infer its structure, its rotation rate, even the pattern of its light. One of the best studied examples is Lumen 16b, part of that binary brown dwarf system, just 6.5 light-years from Earth. In 2013, astronomers using the Very Large Telescope in Chile monitored Lumen 16b over several nights, tracking how its brightness varied. They found periodic changes repeating every 87 hours, the rotation period of the brown dwarf. By analyzing these variations in detail, they reconstructed a rough map of its surface, showing bright and dark patches moving across the hemisphere. What they found was striking. Lumen 16b's atmosphere isn't uniform. It has regions of thick clouds and regions of clearer atmosphere. The clouds are likely made of iron and silicate dust, condensed out of the gas at temperatures around 1,000 to 1,300 Kelvin. These aren't water clouds like on Earth. They're clouds of molten iron droplets and mineral dust drifting through an atmosphere that's hundreds or thousands of degrees hotter than any place on our planet. Think about that for a moment. Clouds made of iron, floating in a sky that would vaporize any spacecraft we could build. It's the kind of environment that challenges our imagination, that forces us to expand our concept of what weather can be. The winds on brown dwarfs are also extreme. Computer simulations suggest that brown dwarf atmospheres experience winds exceeding 1,000 kilometers per hour, possibly reaching several thousand. For comparison, the fastest winds in Earth's atmosphere, found in jet streams and inside the most powerful hurricanes, top out around 400 kilometers per hour. Brown dwarf winds are several times faster, driven by differential heating between the equator and poles, and by the rapid rotation of the object. Most brown dwarfs rotate in just a few hours. Some complete a full rotation in as little as 2 or 3 hours. This rapid spin creates powerful Coriolis forces, deflecting winds and creating complex circulation patterns. The result is banded structures similar to what we see on Jupiter and Saturn, but even more dynamic. Bands of eastward and westward winds separated by narrow shear zones where storms form and evolve. Scientists believe that these circulation patterns can create persistent storm systems, cyclones and anticyclones that last for years or even decades. Unlike Earth's hurricanes, which derive energy from warm ocean water and dissipate over land, brown dwarf storms are powered by internal heat. They don't need external energy sources. They just keep going, fed by the brown dwarf's slow cooling. One fascinating aspect of brown dwarf weather is the role of temperature gradients. In a brown dwarf's atmosphere, temperature decreases with altitude just like on Earth. But the scale is different. The upper atmosphere might be a few hundred degrees cooler than the deeper layers. This creates convection-rising plumes of hot gas and descending streams of cooler gas. It's similar to convection in Earth's atmosphere, which drives thunderstorms and trade winds. But the energy involved is much greater. Research shows that convection in brown dwarf atmospheres can create updrafts and downdrafts moving at hundreds of kilometers per hour. These vertical winds transport heat from the interior to the surface where it radiates into space. They also loft dust grains high into the atmosphere, where they can drift laterally before falling back down. This process creates patchy cloud cover regions where dust is thick and regions where it's thin or absent. The result is an atmosphere that's constantly churning, constantly rearranging itself, never still, never uniform, always in motion. There's also the intriguing possibility of precipitation on brown dwarfs. Not rain as we know it, but something analogous. In the cooler brown dwarfs, T and Y types, temperatures can drop low enough for more exotic materials to condense. Water can condense into clouds at around 400 Kelvin. Ammonia condenses even cooler, around 200 Kelvin. Scientists suggest that in the coolest Y dwarfs you might have clouds of water ice or ammonia ice, and when conditions are right, these particles might grow large enough to fall, creating a kind of rain or snow. Imagine it, snowflakes of water ice or ammonia, crystals drifting down through a thick atmosphere, illuminated faintly by the infrared glow of the brown dwarf itself. It would be silent, slow, eerily beautiful. A perpetual winter without ground to accumulate on. The snow would fall until it reached warmer layers below, where it would evaporate and rise again only to condense and fall once more. An endless cycle. Have you ever stood in falling snow and felt the stillness it brings? The way sound seems muffled, the world softened. Brown dwarf snow might feel different, heavier perhaps in the strong gravity. But the sense of quiet motion of particles descending through atmosphere might be similar. Though, of course, you could never actually stand there. The gravity would crush you. The heat would incinerate you. The lack of solid ground would leave you falling forever. But it's a lovely thought. One of the surprises in brown dwarf meteorology has been the discovery of variability. Some brown dwarfs show very consistent brightness variations, rotating like clockwork, suggesting stable cloud patterns. Others are more erratic with brightness changes that shift over time. This variability indicates evolving weather storms that grow and shrink cloud decks that form and dissipate. In 2017, astronomers studying a brown dwarf called 2MASSJ 2139276 plus 0220226 noticed that its brightness variations changed significantly over several years. The cloud patterns weren't static. They were evolving, driven by processes we don't fully understand. Maybe it's seasonal changes, though. Brown dwarfs don't orbit stars and don't have seasons in the traditional sense. Maybe it's long-term cycles in atmospheric circulation, analogous to Earth's El Niño or decadal oscillations. We're still learning. This unpredictability makes brown dwarfs endlessly fascinating. They're not just objects to catalog and classify. They are dynamic, changing, alive in a metaphorical sense. They have moods if weather can be thought of as mood. Some days they're cloudy, other days clearer. The light they emit varies not because they're unstable internally, but because their surfaces are complex, textured, shifting. There's also the question of atmospheric composition and how it affects weather. Brown dwarfs have atmospheres rich in hydrogen and helium, with traces of heavier elements like carbon, nitrogen, oxygen. These elements combine to form molecules: methane, water, ammonia, carbon monoxide. Each molecule has different condensation temperatures, different opacities, different behaviors. As a brown dwarf cools, different molecules become important at different times. In hot L, dwarfs, the atmosphere is dominated by dust iron silicate aluminum oxide. This dust absorbs light, heating the upper atmosphere and creating a temperature inversion where temperature actually increases with altitude. This inversion can suppress convection in some regions, creating stable cloud decks. As the brown dwarf cools into the T-dwarf range, the dust settles out and methane takes over. The atmosphere clears, convection becomes more vigorous, and weather patterns change. It's like watching a planet evolve and fast forward, passing through different climatic regimes as it ages, from dusty to clear, from chaotic to structured, or vice versa. The details depend on the brown dwarf's mass rotation rate, initial composition. No two brown dwarfs follow exactly the same path. Scientists use computer models to simulate brown dwarf atmospheres, trying to reproduce the observed weather patterns. These models solve equations of fluid dynamics, thermodynamics, radiative transfer chemistry. They're incredibly complex, requiring supercomputers to run. But they've been remarkably successful, capturing many of the observed features, the banded structures, the persistent storms, the variability. Yet, mysteries remain. Some observations don't match the models. Some brown dwarfs are brighter or dimmer than expected. Some show evidence of strong vertical mixing, churning the atmosphere so effectively that it should homogenize, yet it remains patchy. Nature, it seems, is always a step ahead of our theories. One common misconception is that brown dwarfs are calm, dead objects. After all, they're not fusing hydrogen. They're cooling, fading. Shouldn't they be quiet? But the opposite is true. Brown dwarfs are meteorologically active with weather systems, as intense as any in the solar system, maybe more so. The lack of fusion doesn't mean lack of activity. Internal heat, rapid rotation, and atmospheric chemistry all combine to create dynamic, ever-changing environments. Another misconception is that brown dwarf weather is chaotic and unpredictable. In fact, many brown dwarfs show highly regular variability, suggesting well-organized circulation patterns. The weather is complex, yes, but not random. It follows physical laws, responds to forces in predictable ways. We're learning to read the patterns to understand the rhythms. There's beauty in that understanding, in realizing that even objects as alien as brown dwarfs obey the same fundamental principles that govern Earth's weather. Pressure gradients drive winds. Temperature differences create convection. Rotation deflects flow. The scales are different, the materials are exotic, but the physics is universal. And here's something poignant. Brown dwarfs will continue to have weather for billions of years, long after they've cooled to planetary temperatures. Even a Y dwarf at 250 Kelvin colder than Antarctica still has. An atmosphere still has circulation driven by residual internal heat and rotation. The storms won't be as violent, the winds slower, but they'll persist. Weather without end on worlds, without surfaces under skies, with no stars to light them. It's a kind of eternity, quiet and dark, but never still. Always moving, always changing, always weathering the passage of time in the only way a brown dwarf knows how. With winds that never rest, clouds that never fully clear, cycles that spiral on across the ages. But weather isn't the only unexpected phenomenon brown dwarfs revealed to us. Because as astronomers listened more carefully, they discovered something else whispers in the radio. spectrum faint but unmistakable, hinting at forces even more powerful than wind. There's a kind of light we can't see, a kind of energy that passes through us constantly, without leaving a trace. Radio waves. They carry voices across continents, images across oceans, whispers from the depths of space. And in the early 2000s, when astronomers pointed radio telescopes at brown dwarfs expecting silence, they heard something unexpected. Bursts of energy, pulses, static crackling across frequencies. The fail stars were speaking not in visible light, but in radio. And what they were saying changed everything we thought we knew about them. They weren't dead. They were singing. The discovery of radio emission from brown dwarfs came as a surprise. Radio waves from astronomical objects usually indicate one of several things: hot plasma, like in stars, synchrotron radiation, from relativistic particles spiraling in magnetic fields, or auroral processes similar to those on Earth. But brown dwarfs weren't supposed to have any of these. They're too cool for hot plasma. They don't have the energetic environments that create synchrotron radiation. And auroras require magnetic fields and charged particles, which, well, okay, brown dwarfs might have those. But no one expected them to be strong enough to detect from Earth. In 2001, a team of astronomers using the Very Large Array Radio Telescope in New Mexico detected radio emission from a brown dwarf called LP944-20. This was unexpected. Follow-up observations confirmed it wasn't a fluke. Other brown dwarfs were found to emit radio waves as well, many of them pulsing in regular bursts, repeating every few hours as the brown dwarf rotated. The signal was clear, unmistakable, puzzling. What could cause this? Research shows that brown dwarfs possess surprisingly strong magnetic fields. Not as strong as neutron stars, which have the most intense magnetic fields in the universe, but much stronger than astronomers initially expected for objects with no nuclear fusion. Magnetic field strength in brown dwarfs has been measured at thousands of Gauss, comparable to the strongest sunspots on the sun, but covering the entire surface. For comparison, Earth's magnetic field is about half a Gauss. Brown dwarfs are magnetically powerful. The origin of these magnetic fields lies in the brown dwarf's interior. Even though they're not fusing hydrogen, brown dwarfs are still partially ionized inside. They're hot enough that electrons are stripped from atoms, creating a soup of charged particles of plasma. This plasma is electrically conductive, and when a conductive fluid moves, especially when it rotates rapidly, it can generate magnetic fields through a process called a dynamo. This is the same mechanism that creates Earth's magnetic field. Molten iron in Earth's outer core rotating with the planet generates currents that produce magnetism. Brown dwarfs work similarly, but on a much larger scale. Their entire interiors, massive and rotating in just a few hours, act as giant dynamos churning out magnetic fields that thread through the atmosphere and extend into space. Scientists suggest that these magnetic fields interact with the brown dwarf's atmosphere in complex ways. Charged particles, electrons, and ions get trapped in the magnetic field lines, spiraling around them like beads on a wire. As the brown dwarf rotates, the magnetic field sweeps through space, and something remarkable happens. The charged particles accelerate, gaining energy, and as they spiral, they emit radiation. At certain frequencies, this radiation is in the radio spectrum. The brown dwarf becomes a radio beacon, pulsing with every rotation. This process is similar to what happens in Earth's auroras. In the polar regions, Earth's magnetic field channels charge particles from the solar wind down into the upper atmosphere, where they collide with air molecules, creating the shimmering curtains of light we call the northern and southern lights. Brown dwarfs might have analogous phenomena, but instead of visible light, they produce radio emission. Auroras without atmosphere, in a sense. Magnetic light. One of the most intensely studied radio-emitting brown dwarfs is TVLM 513-46546. This object, discovered in the TVLM survey, is about 75 Jupiter masses right near the hydrogen burning limit. It emits regular radio bursts every 2 hours, corresponding to its rotation period. The radio emission is highly polarized, meaning the radio waves oscillate in a specific direction, another signature of magnetic processes. By studying TVLM 513 over many observations, astronomers have mapped its magnetic field structure. The field isn't uniform. It has complex geometry with regions of stronger and weaker magnetism, possibly with multiple magnetic poles. As the brown dwarf rotates, different parts of the magnetic structure swing into view, producing variations in the radio signal. It's like a lighthouse, but instead of a beam of visible light, it's a beam of radio waves sweeping through space. The fact that brown dwarfs have such strong magnetic fields raises interesting questions. Magnetic fields in stars are thought to be generated by convection and differential rotation, different layers rotating at different speeds. But brown dwarfs, especially cooler ones, might not have vigorous convection. How then do they sustain these fields? Some scientists believe it's related to their rapid rotation. Others point to residual heat driving subtle convection. The truth is, we don't fully understand it yet. The dynamo mechanism in brown dwarfs is still an active area of research. There's also the question of whether brown dwarfs can have magnetospheres, regions of space dominated by the magnetic field. Planets like Earth and Jupiter have magnetospheres that shield them from the solar wind. Brown dwarfs floating free in interstellar space don't have a stellar wind to shield against. But they do have magnetic fields extending outward, creating zones where charged particles are trapped and accelerated. These might be thought of as magnetospheres without a planet beneath them, magnetic bubbles floating in the void. Imagine that, a sphere of magnetic force invisible to the eye, stretching thousands of kilometers around a brown dwarf. Particles racing along field lines, emitting radiation, creating currents of energy in empty space. It's a hidden architecture, a structure built not of matter, but of force. And we can detect it across light years by listening to the radio whispers it produces. Have you ever tuned an old radio and heard static between stations that hiss and crackle, the noise of random electromagnetic waves filling the air? Brown dwarf radio emission isn't random like that. It's structured, pulsing rhythmic, but it shares that quality of being something you hear rather than see, something that reveals itself through a different sense. Astronomers are learning to listen to the universe, not just look at it. One fascinating aspect of brown dwarf magnetism is its potential connection to auroral activity. On Earth, auroras occur when solar wind particles interact with our magnetic field and atmosphere. But brown dwarfs don't have solar wind, and their atmospheres are more like the outer layers of a star. So, where do the charged particles come from? Scientists suggest several possibilities. One is that the brown dwarf itself is the source. Material from the upper atmosphere might be ionized by heat or radiation, and these particles get caught in the magnetic field, accelerating and emitting radiation. Another possibility is cosmic rays, high-energy particles from space that constantly bombard all objects. These cosmic rays could interact with the brown dwarf's magnetic field, contributing to the radio emission. A third, more speculative idea involves magnetic reconnection. This is a process where magnetic field lines break and reconnect, releasing stored magnetic energy explosively. It happens on the sun during solar flares. If brown dwarfs undergo similar reconnection events, they could accelerate particles to high energies, producing bursts of radio emission. Some of the observed variability in brown dwarf radio signals might be evidence of this. The study of brown dwarf magnetism also has implications for understanding exoplanets. Many exoplanets are gas giants, similar in composition to brown dwarfs. If these planets have strong magnetic fields, they might also emit radio waves. Detecting radio emission from an exoplanet would be a major breakthrough, providing information about the planet's interior rotation and magnetic environment. Brown dwarfs serve as test cases, teaching us what to look for how to interpret the signals. In 2015, astronomers detected what might be the strongest magnetic field ever measured on a brown dwarf on an object called 2MA SSJ 052333822-1403022. The field strength was estimated at several kilogauss, several thousand times stronger than Earth's field. At these strengths, magnetic forces become significant even on large scales. They can influence atmospheric circulation, suppress convection in some regions, or even affect the brown dwarf's rotation over long time scales. There's something almost eerie about the idea of invisible magnetic forces shaping these objects, guiding particles, storing energy. You can't see a magnetic field directly. You infer it from its effects. On brown dwarfs, we infer it from radio emission, from spectral features from modeling. It's a hidden layer of reality, accessible only through indirect means. One common mistake people make is assuming that because brown dwarfs don't fuse hydrogen, they are magnetically inactive. The opposite is true. Magnetic activity seems to persist across a wide range of brown dwarf temperatures and masses. Even very cool T and Y dwarfs with temperatures below 1,000 Kelvin might have magnetic fields, though detecting them is harder because cooler objects rotate more slowly and might produce weaker radio emission. Another misconception is that magnetic fields require a solid core like Earth's iron core, but brown dwarfs are entirely gaseous or at least fluid throughout their interiors. There's no solid core. The dynamo operates in the fluid itself, driven by convective motion and rotation. It's a different kind of dynamo than Earth's, but no less effective. The interplay between magnetic fields and atmospheric weather on brown dwarfs is also an area of active research. On Earth, magnetic fields don't significantly affect weather because atmospheric forces are much stronger. But on brown dwarfs, where magnetic fields can be thousands of Gauss, the magnetic pressure might be comparable to gas pressure in the upper atmosphere. This could create magnetically active regions, similar to sunspots where convection is suppressed and the atmosphere is cooler or hotter than surroundings. Scientists believe that these active regions might contribute to the observed variability in brown dwarf brightness and spectra. As the brown dwarf rotates, magnetically active regions swing in and out of view, changing the overall appearance. Weather and magnetism become intertwined, two aspects of the same dynamic atmosphere. There's also the tantalizing possibility of magnetic storms on brown dwarfs. On Earth, geomagnetic storms occur when disturbances in the solar wind interact with our magnetic field, causing auroras and disrupting technology. On brown dwarfs, magnetic storms might be internal, driven by changes in the dynamo or by magnetic reconnection. These storms could release bursts of energy, temporarily brightening the radio emission or causing flares. Flares on brown dwarfs have been observed. Sudden intense bursts of radio emission, lasting minutes to hours, then fading back to baseline. They're reminiscent of solar flares, but happening on objects with no nuclear fusion. The energy comes from the magnetic field itself, from the reconfiguration of field lines and the acceleration of particles. It's a reminder that brown dwarfs, for all their stillness and cooling, are far from inactive. They're dynamic, evolving, energetic. What would it be like to witness a brown dwarf flare up close? You wouldn't see visible light, but if you had eyes sensitive to radio frequencies, you might perceive a sudden brightening, a pulse of energy washing over you. Charged particles racing outward from the brown dwarf, following invisible magnetic highways. It would be silent in the vacuum of space, but powerful nonetheless. A storm of energy in the dark. The magnetic fields of brown dwarfs might also have implications for habitability, though brown dwarfs themselves are unlikely to host life. But if a brown dwarf has companions, planets, or moons, those companions would be bathed in the brown dwarf's magnetic environment. Strong magnetic fields could strip away atmospheres from nearby planets, or conversely, they might protect them from cosmic rays. The details depend on the configuration, the distances, the strengths involved. It's speculative, but it's worth considering. The universe is full of brown dwarfs, and some of them might have planetary systems. Understanding their magnetic environments helps us understand what those systems might be like. As we listen to the radio whispers from brown dwarfs, we're learning that these objects are far more complex than we imagined. They're not just cooling embers fading into obscurity. They're magnetically active, dynamically evolving, broadcasting their presence across the electromagnetic spectrum. They challenge us to see them not as failed stars, but as a unique category of object, with their own behaviors, their own mysteries. And every mystery solved leads to deeper questions. If brown dwarfs have magnetic fields this strong, what else are they capable of? What other phenomena remain undiscovered, waiting for the right instruments, the right questions? The radio emission was a surprise. What surprises lie ahead? But beyond the immediate puzzles of magnetism and weather, brown dwarfs hold another kind of significance. They're not just objects to study for their own sake. They're archives, time capsules, witnesses to the universe's history, carrying information that goes far beyond their individual existence. Some things in the universe change so slowly, they become witnesses to time itself. Mountains on Earth rise and erode over millions of years, preserving layers of ancient rock stories written in stone. Brown dwarfs do something similar, but on cosmic scales. They form, they cool, and as they cool, they preserve the chemical fingerprint of the cloud that made them. Unchanged, unaltered, like fossils, but fossils of the universe's youth drifting through space, carrying secrets about where we all came from. And we're learning to read what they remember. Unlike stars which transform their interiors through fusion mixing elements, creating new ones, brown dwarfs are largely static after their brief deuterium-burning phase ends. Their composition stays frozen. The hydrogen, helium, and trace elements they gathered during formation remain in roughly the same proportions, billions of years later. There's no nuclear alchemy happening inside, no stellar processing turning hydrogen into helium, into carbon, and beyond. What you see chemically speaking is what you get. A snapshot of the cloud they came from, preserved in their atmospheres. This makes brown dwarfs invaluable for understanding the chemical evolution of the galaxy. Every generation of stars enriches the interstellar medium with heavier elements, what astronomers call metals, even though that includes things like carbon and oxygen. When massive stars explode as supernovae, they scatter these metals into space, where they mix with the hydrogen and helium and eventually get incorporated into new stars and brown dwarfs. By measuring the metal content of a brown dwarf, scientists can infer when it formed and what the galaxy's chemical composition was at that time. Research shows that brown dwarfs can be age-dated using several methods. One involves measuring lithium abundance in their spectra. Lithium is a fragile element easily destroyed by nuclear reactions at relatively low temperatures. In stars, lithium gets depleted as the star ages, burned away in the hot interior. But in brown dwarfs, especially those below about 65 Jupiter masses, lithium survives because the interior never gets hot enough to destroy it. By looking at how much lithium remains and comparing it to theoretical models of depletion, astronomers can estimate the brown dwarf's age. Older brown dwarfs have had more time to deplete their lithium, though the depletion is slow and subtle. Younger ones still retain most of their initial lithium. It's like counting tree rings, except the rings are measured in spectral lines, and the tree is a failed star floating in the void. Another method involves looking at the brown dwarf's kinematics, its motion through space. Older objects tend to have higher velocities relative to the galactic disk, because they've had more time to be perturbed by gravitational interactions with other stars and giant molecular clouds. Younger brown dwarfs recently formed in star-forming regions move more sedately. By measuring the brown dwarf's proper motion and radial velocity, astronomers can estimate whether it's part of the young disk population or the older thick disk or halo populations. There are brown dwarfs out there drifting through the Milky Way's halo that are 10 billion years old or more. They formed when the galaxy was young, when the first generations of stars were still enriching the interstellar medium. Their metal content is low, reflecting the lower abundance of heavy elements in the early universe. Studying these ancient brown dwarfs is like holding a piece of the primordial galaxy, something that hasn't changed fundamentally since the cosmos was a fraction of its current age. Scientists believe that brown dwarfs also help us understand the initial mass function, the distribution of masses for objects that form from collapsing gas clouds. In any star-forming region, you get a range of masses. A few massive stars, more intermediate mass stars, many low-mass stars, and a substantial number of brown dwarfs. The initial mass function describes this distribution statistically, but measuring it accurately is difficult because low-mass objects are faint and hard to detect. Brown dwarfs, being at the low end of the mass spectrum, are crucial for constraining the initial mass function. By conducting deep surveys of nearby star-forming regions and counting how many brown dwarfs form relative to stars, astronomers refine their understanding of how mass is distributed during the collapse of molecular clouds. This in turn informs theories of star formation, planet formation, and galactic evolution. One surprising finding is that brown dwarfs can form in isolation, not just in star-forming clusters. Some brown dwarfs are found far from any stellar nursery, drifting alone through the galaxy. How did they get there? One possibility is that they formed in clusters and were ejected through gravitational interactions, flung out into space by close encounters with other forming stars. Another possibility is that they formed in very small, isolated cloud fragments, mini-collapses, that never gathered enough material to make a star. Either way, the existence of isolated brown dwarfs tells us that star formation is more chaotic and diverse than we sometimes assume. It's not a neat, orderly process. It's messy, stochastic, full of chance encounters and unexpected outcomes. There's also the role brown dwarfs play in understanding exoplanets. Many exoplanets discovered by transit surveys and radial velocity studies are gas giants similar in size and composition to Jupiter, but orbiting much closer to their stars. These hot Jupiters have atmospheres that are difficult to study because the glare of the parent star overwhelms the planet's faint light. But brown dwarfs, which aren't orbited by bright stars, can be studied in isolation. Their atmospheres are accessible to detailed spectroscopy. By observing brown dwarfs across a range of temperatures and masses, astronomers build models of how gas giant atmospheres behave. These models are then applied to exoplanets. If a brown dwarf at 1000 Kelvin shows methane absorption and patchy clouds, we expect a gas giant exoplanet at the same temperature to behave similarly. Brown dwarfs serve as proxies laboratories for testing theories that can't easily be tested on the planets themselves. In recent years, the James Webb Space Telescope has begun observing brown dwarfs with unprecedented sensitivity and resolution. Webb's infrared instruments can detect the faintest, coolest brown dwarfs pushing into the Y dwarf regime, where temperatures approach room temperature. These observations reveal fine details in spectra, identifying specific molecules like water methane, ammonia, and even more complex compounds. Each detection refines our understanding of atmospheric chemistry at low temperatures. One of Webb's early targets was the brown dwarf VHS 1256, maybe a young warm object about 40 light-years from Earth. Webb's spectrum revealed silicate clouds, water vapor, methane, and carbon monoxide, all swirling in a turbulent atmosphere. The data was so detailed that scientists could see features never before, resolve validating some models and challenging others. It's the beginning of a new era in brown dwarf studies, where we can probe these objects almost as if we were sending spacecraft to visit them. Have you ever found an old photograph, something from decades ago, and realized it captured a moment that's otherwise lost to time? Brown dwarfs are like that. They're photographs of the galaxy's past chemical snapshots that preserve information long after the stars around them have evolved and changed. They don't create new elements. They don't explode. They just exist quietly, holding on to their initial composition, waiting for us to ask them what they remember. Another lesson brown dwarfs teach us is about the diversity of planetary systems. Some brown dwarfs have been found with disks of dust and gas around them, similar to the protoplanetary disks around young stars. This suggests that planets might form around brown dwarfs, though such planets would be dim and cold, far from any significant source of heat or light. A few candidate planets have been detected orbiting brown dwarfs, though confirming their existence is difficult. If planets do form around brown dwarfs, what would those worlds be like? The brown dwarf provides little warmth, certainly nothing like the sun. Any planet would be frozen dark, illuminated only by the faint infrared glow of the brown dwarf itself. But the planet might have internal heat from radioactive decay or tidal forces if it's in a close orbit. Life as we know it seems unlikely, but the universe has surprised us before. There's also the question of brown dwarf binaries and how they form. As we mentioned earlier, some brown dwarfs orbit each other in pairs. How do two substellar objects end up bound together? Do they form from the same cloud fragment collapsing simultaneously like binary stars? Or do they form separately and later capture each other through gravitational interaction? Observations suggest both mechanisms are possible depending on conditions. Studying binary brown dwarfs allows astronomers to measure masses directly using orbital dynamics. By observing how the two objects orbit their common center of mass, applying Kepler's laws, we can calculate their individual masses. This is one of the few ways to get accurate mass measurements for brown dwarfs, and it's crucial for testing evolutionary models. If the models predict a certain brightness and temperature for a given mass and age, we can check those predictions against real measurements. Scientists have found that some brown dwarf binaries are very wide, separated by hundreds of astronomical units, while others are extremely close, orbiting each other in just a few days. The range is enormous, and it challenges our understanding of how such systems form and remain stable. Close binaries might have formed close or migrated inward over time. Wide binaries might be the result of gentle cloud fragmentation or capture events in crowded environments. One common mistake is assuming that all brown dwarfs are isolated, lonely wanderers. In fact, many brown dwarfs have companions, other brown dwarfs, low-mass stars, even planets. The universe doesn't isolate objects as neatly as we might think. Gravitational interactions bind things together in complex hierarchies, and brown dwarfs participate in that dance. Another misconception is that brown dwarfs are useless for astrobiology. While it's true they don't provide much energy for life, their existence expands the parameter space for habitability. If rogue planets can have subsurface oceans heated by internal processes, maybe planets around brown dwarfs can too. Maybe life doesn't need a star. Maybe all it needs is the right chemistry, the right environment, and time. It's speculative, but brown dwarfs remind us to keep an open mind. The universe is stranger and more varied than our imaginations. Brown dwarfs also contribute to the galaxy's dark matter inventory, though not in the way once thought. In the 1990s, some astronomers speculated that dark matter might be composed of massive compact halo objects, or machos, including brown dwarfs. If the galaxy were filled with unseen brown dwarfs, they could account for the missing mass inferred from galactic rotation curves. Surveys were conducted looking for gravitational microlensing events where a brown dwarf passing in front of a distant star would briefly magnify its light. The results were conclusive. Brown dwarfs are too rare to be dark matter. There aren't enough of them to account for the missing mass. Dark matter is something else, likely exotic particles rather than ordinary matter. But the surveys weren't in vain. They found some brown dwarfs, refined our census of the local galaxy, and ruled out one hypothesis, clearing the way for better theories. That's how science progresses. Not every idea is correct, but testing ideas, even incorrect ones, leads to knowledge. Looking forward, the next generation of telescopes will revolutionize brown dwarf studies. Instruments like the Extremely Large Telescope, currently under construction in Chile, will have the resolution and sensitivity to study brown dwarf atmospheres in exquisite detail. We'll see weather patterns evolve in real time, measure chemical abundances of rare isotopes, maybe even detect auroras in optical or ultraviolet light. We'll also find more brown dwarfs, especially the coolest and oldest ones. As infrared surveys become more sensitive, the census will grow and will map the brown dwarf population across the galaxy. We'll learn how common they are, how their formation varies with environment, and how they've contributed to the galaxy's structure over billions of years. There's even talk of sending spacecraft to study nearby brown dwarfs up close. Lumen 16, at just 6.5 light-years, is tantalizingly close in cosmic terms, though still far beyond our current propulsion capabilities. But in a future where interstellar travel becomes feasible, brown dwarfs would be among the first targets. Imagine a probe arriving at a brown dwarf, deploying sensors, measuring its magnetic field, directly sampling its upper atmosphere, mapping its clouds in high resolution. The data would transform our understanding. Until then, we study them from afar, piecing together their stories. From the light they emit the radio waves, they broadcast the gravitational tugs they exert on companions. It's detective work puzzles solved one clue at a time. And brown dwarfs are generous with clues. They reveal their temperatures, their compositions, their ages, their motions. They tell us about the galaxy's history, the processes of star formation, the boundaries of planetary science. They're fossils, yes, but fossils that are still alive, in a sense. Still cooling, still rotating, still radiating. Still offering lessons to anyone willing to listen. And as we listen, as we gather data and refine theories, we realize something profound. Brown dwarfs aren't footnotes in the cosmic story. They're chapters integral to understanding how the universe works, how matter behaves, how the space between stars is populated. They failed to become stars, but in that failure, they became something uniquely valuable. Teachers, archives, windows into physics and chemistry we can't replicate on Earth. They remind us that success and failure are human judgments irrelevant to the universe. What matters is existence, the fact of being the contribution each object makes to the grand tapestry. Brown dwarfs exist, and in existing, they matter. They illuminate the darkness not with visible light, but with knowledge, with the information they carry, with the questions they inspire. And perhaps, that's the greatest lesson of all, that meaning doesn't require burning bright, that value can be quiet, subtle, patient, that even the things that almost were can teach us about what is. We've come a long way through the darkness, you and I. We've drifted past objects that almost became stars that gathered and heated and reached for ignition, but fell short. We've watched them cool through spectral phases seen. Storms rage in their atmospheres, heard their radio whispers across the void. We've learned that brown dwarfs are more than cosmic footnotes. They're witnesses, teachers, mysteries wrapped in infrared glow. And now, as our journey together draws to a close, it's worth asking one final question. What does it mean to be a brown dwarf? What does it mean to exist in the space between? Perhaps the answer is simpler than we think. Throughout human history, we've celebrated the bright and the loud, the stars that blaze across the night sky, the planets that wander visibly against the constellations, the supernovae that announce themselves across galaxies. We build our myths around the spectacular, the undeniable, the things that demand to be seen. And there's nothing wrong with that. Brightness has its place. But brown dwarfs remind us that the universe is also filled with the quiet, the subtle, the things that exist without fanfare. They don't burn hydrogen. They don't illuminate planets. They don't create the heavy elements that make life possible. They just exist, cooling slowly, rotating in the dark, carrying their histories with them. And somehow, that's enough. They don't need to justify their existence with light or heat or fusion. They simply are, and in being, they contribute to the cosmos in ways we're only beginning to understand. Scientists estimate there could be tens of billions of brown dwarfs in our galaxy, alone, maybe more. They've been there all along, invisible to our eyes, waiting for us to develop the technology to see them. And when we finally learned to look in infrared, we found a population as rich and diverse as the stars themselves. Young ones and old ones, hot ones and cold ones, isolated wanderers and binary companions. Each one unique, each one carrying its own story. What strikes me most about brown dwarfs is their patience. They form over hundreds of thousands of years, cool over billions, and will continue to exist long after our sun has died. A brown dwarf born today will still be glowing faintly when the universe is twice its current age. It will outlast civilizations, galaxies, maybe even clusters of galaxies. It will drift through the expanding cosmos, growing colder and dimmer, but never quite disappearing, never quite giving up. There's a kind of quiet dignity in that, don't you think? To endure without recognition, to persist without purpose, to simply be. Because being is what you do. Brown dwarfs don't strive, they don't aspire, they don't measure themselves against stars and find themselves lacking. They just exist on their own terms, following the laws of physics to their inevitable conclusions. In many ways, they are perfect metaphors for existence itself. Not everything needs to shine to matter. Not everything needs to burn to be real. Some things just need to occupy space, to move through time, to interact with the universe in small, subtle ways. And those small interactions add up. The gravitational pull of a brown dwarf affects the orbits of nearby objects. Its magnetic field channels particles. Its infrared glow warms however faintly the space around it. It's part of the cosmic web, connected to everything else through gravity and radiation and the simple fact of presence. Have you ever felt like you weren't enough, like you were meant for something greater but fell short? Brown dwarfs know that feeling intimately. They were meant to be stars. The physics was there. The potential was there. But circumstances, mass timing, environment kept them from crossing that threshold. And yet they endure. They adapt. They become something else, something unexpected, something valuable in its own way. Maybe that's the real lesson they offer, that falling short of one goal doesn't mean failure. It just means a different path, a different outcome. Brown dwarfs didn't become stars, but they became brown dwarfs, and that's its own kind of achievement. They exist in a realm no star can occupy, too cool and too massive for any stellar category. They're unique, and uniqueness has value even when it's not celebrated. Research into brown dwarfs continues to accelerate. Every year brings new discoveries, new insights, new questions. We're finding cooler brown dwarfs, older ones with unexpected chemical compositions or surprising magnetic activity. We're mapping their weather, measuring their masses, cataloging their populations across the galaxy. Each data point refines our understanding, and each refinement reveals new mysteries. The James Webb Space Telescope is currently observing some of the coldest brown dwarfs known, peering into their atmospheres with unprecedented detail. We're seeing molecules we've never detected before, cloud structures we didn't predict, variability on timescales that challenge our models. It's exciting, humbling, inspiring. The more we learn, the more we realize how much we don't know. And that's okay. Science isn't about having all the answers. It's about asking better questions, refining our methods, remaining open to surprise. Brown dwarfs have surprised us repeatedly. They've challenged our definitions, exceeded our expectations, revealed phenomena we didn't anticipate. They'll likely continue to surprise us for decades to come. There's also something deeply human about our fascination with brown dwarfs. We see ourselves in them in a way. Objects that didn't quite achieve their intended purpose, but found meaning nonetheless. We're all in some sense failing at something, falling short of some ideal. But, like brown dwarfs, we persist. We cool and dim over time, yes, but we also carry our histories with us. We're shaped by where we came from, what we've experienced, the people and places that formed us. Brown dwarfs preserve the chemical fingerprint of their birth clouds. We preserve memories, lessons, scars, joys. We're time capsules too, in our own way. And just as brown dwarfs can teach astronomers about the galaxy's past, we can teach others about our own pasts, sharing knowledge, passing down stories, contributing to the collective understanding of what it means to be human. The parallels aren't perfect, of course. Brown dwarfs don't have consciousness, don't reflect on their existence, don't wonder what they might have been. But we do. And maybe that's our gift and our burden. The ability to contemplate what we are, what we wanted to be, what we became instead. Brown dwarfs just exist. We exist and think about existing. Both are valid, both matter. As we close this journey, I want you to imagine one more time a brown dwarf floating alone in the space between stars. It's old, now cool to just a few hundred degrees above absolute zero. It's been drifting for 10 billion years, since the galaxy was young, since stars were just beginning to form in great numbers. It's outlived countless generations of stars. It's seen the universe change, expand, evolve. And through it all, it's remained essentially the same. Cooling, yes. Dimming, yes. But still itself. Still a brown dwarf. If it could speak, what would it say? Maybe nothing. Maybe silence is its language and patience its message. Or maybe it would say what all enduring things say in their way. I am here. I was here. I will be here. That's enough. Scientists believe that in the far future, trillions of years from now, when the last stars have burned out and the universe has cooled to near uniformity, brown dwarfs will still exist. They'll be cold, then colder than anything we can easily imagine, but they'll be there. Remnants of an earlier, brighter age. Final witnesses to a universe that once glowed with starlight. And eventually, even they will fade into the darkness, their last photons escaping into an ever-expanding void. But that's so far in the future, it's almost abstract. For now, brown dwarfs are warm. They're glowing. They're observable. They're teaching us about physics and chemistry and the nature of matter. They're expanding our understanding of what's possible, what exists, what the universe contains. They're part of the present, not just the past or the distant future. They're alive in the cosmic sense. And we're alive too, you and I, here in this moment, contemplating objects we'll never see with our eyes, understanding them through mathematics and spectroscopy and imagination. It's a remarkable thing, really. The human mind reaching across light years, touching the intangible, finding meaning in the faint infrared glow of failed stars. We're connected to brown dwarfs through curiosity, through science, through the simple fact that we're all made of stardust, all products of the same cosmic processes. You were born from elements forged in stars and supernovae. Brown dwarfs were born from clouds enriched by those same stars and supernovae. We're cousins in a way. Distant, yes. Different, certainly. But related nonetheless. Part of the same family, the same universe, the same grand story. So, what do we take away from this? What do brown dwarfs teach us, ultimately? Maybe just this existence doesn't require justification. You don't have to shine brightly to matter. You don't have to achieve fusion to have value. You can exist quietly in the margins, doing what you do, being what you are. And that's enough. It's always been enough. The stars will shine, the galaxies will spin, the universe will expand, and the brown dwarfs will drift through it all, patient as time, quiet as darkness, warm as distant memory. They'll cool and dim and eventually fade, but not yet. Not for billions of years yet. For now, they glow. Faintly, yes. Invisibly to our eyes. But really, truly, undeniably, they're out there right now as you listen to this. Dozens within 100 light years, hundreds within 1,000, billions across the galaxy. Each one a world unto itself, a mystery, a lesson, a reminder that the universe is richer and stranger than we ever imagined. They were born to be stars, but they became brown dwarfs instead. And in becoming brown dwarfs, they became irreplaceable. We've walked through their story together, from theoretical prediction to discovery, from classification to weather to magnetism to meaning. We've learned that they're not failures, they're variations. They're the universe exploring every possibility, every niche, every way that matter can arrange itself under gravity. They're proof that nature doesn't judge, doesn't compare, doesn't rank. It just creates endlessly everything that can exist. And isn't that beautiful? Isn't that worth celebrating? The brown dwarfs don't celebrate themselves. They don't even know they exist. But we know. We've found them, studied them, named them, wondered about them. We've given them meaning through our curiosity. And in return, they've given us knowledge, perspective, humility. Thank you for drifting here with me, through the darkness, through the stories of stars that never truly shone. Thank you for listening, for wondering, for caring about objects most people will never know exist. You didn't have to be here, but you were. And that means something. Just like brown dwarfs mean something. Just like everything that exists means something in its own quiet way. The universe is vast, and we've only explored one small corner of it tonight. There are more stories waiting, more mysteries to unfold, more quiet wonders hiding in the spaces between the bright things. And when you're ready, when the night feels wide again and curiosity calls, I'll be here ready to drift with you once more into the gentle unknown. Until then, rest easy, dream softly, and remember, the brown dwarfs glowing faintly in the dark, reminding us that light doesn't have to be bright to be real, that warmth doesn't have to burn to be felt, that existence doesn't need to shout to matter. Sleep well, friend, and good night.